So what exactly is a half-life? Well, a half-life is the time taken for half the radioactive nuclei to decay. So, what does this mean? Well, a radioactive material will have some nuclei that are stable and some nuclei that are unstable. So, what this means is that in a particular material, there will be a ton of stable nuclei and some unstable nuclei. Now, the definition of stable means that it doesn't change. So the stable nuclei will actually remain the same. So nothing will change for them. But the unstable nuclei, after undergoing a half-life, will change, or some of them will change. So instead of there being 4 unstable nuclei in this sample, there will be 2, and then the other 2 will turn stable. So, different substances will do this at different rates. So some are able to do it really quickly, while others can take a much longer time. It all depends on the material and its half-life. For example, lithium 8 has a half-life of 0.85 seconds, which is super quick. On the other hand, uranium 238 has a half-life of 4.51 billion years, which is drastically bigger than 0.85 seconds. So, it is important to remember that in the same amount of time, during each half-life, a substance will lose half of its remaining unstable nuclei. So if we go back to the diagrams where green represents stable and blue represents unstable, you'll see that as time goes on, the unstable nuclei will decrease by half each time until there is no more left that is unstable, and as a result, you get a completely stable substance. Now, how to measure a half-life using a graph is something that's super important to something in this unit. So if we're looking at a graph, say something that looks like this, where time will always represent the x-axis, and in this case we'll do days, so 10 days, 20 days, 30 days, 40 days, 50 days, 60 days, and so on. And where the y-axis will represent the count rate. So, on this side, we'll start with 200 and try and go all the way up to 1800. I think that's a good number to stop at. So the easiest way to measure half-life from the graph is to read the original count rate at 0 days. So if this is 0 days right here, we must look at where our first starting point would be, and in this case it would be just above the 1600 at 1640, because that is where our particular material is starting at. So after doing that, you go half the original count rate. So for this example, it'd be 820 down, so you'd mark that at a little over 1,000, because you don't actually go down to 820, you just take the 1640, divide by 2 to get your half-life, and then subtract this number by this number, and you end up just under 1,200. And you just continue the steps, so you'll start at this number, divide by 2, and then subtract this number by the number you just got. And eventually, you will have a graph that will look something like this. And as you can see, it sort of just staggers down. And to help you find the original count rate, you can draw a horizontal line to the curve. So if this is my third one here, you draw one here and one here, and that'll get you your original count rate. And by doing that, you are able to read the half-life where the line crosses the time axis. So on our particular graph, the half-life is supposed to be 20 days, so more like here. If we were to redo this graph, because it's not the most accurate, it would be about here instead, so at 20 days. So to calculate a half-life is another really important step in determining what a half-life is for a certain material. So there are two types of calculations using the half-life. The first one is that if you are given two count rates and you know how long it takes to get from one to the other, then you can calculate the half-life of the material. So what you need to know is two count rates and the time from one to the other. The second way to calculate a half-life is if you know the half-life of the material, you are then able to calculate the count rate, and so that will also determine. So it can go both ways. It all just depends on what you're given. It's typical to most equations used in any sort of math. So an example question would be the half-life of a material is 3 hours. If the initial count rate is 544, what will the count rate be after 15 hours? So in this problem, we're given 3 super important numbers. The first one is the 3, and this represents the amount of hours it takes a certain material to undergo one half-life. The second super important number is 544 because this represents the initial count rate of the certain material. And lastly, it gives us what we are trying to find, and so it's asking us what would the count rate be after 15 hours. Now these 3 numbers are super important because they will all be needed in the equation. So we are told that the half-life of the material is 3 hours once again, and in 15 hours there are 15 divided by 3 half-lives, or 5 half-lives. So after each half-life, the count rate is going to be divided in half. So to figure out how to do a problem like this, you can use a box method. So you start out with the initial count rate, which is again 544, and you're just going to box that. And you're going to draw an arrow which counts as one half-life. So you will put a number 1 to represent that that is one half-life that just went on. And so to calculate that half-life, you'll have to do 544 divided by 2. 544 divided by 2 is 272. Once again, you'll box it and draw an arrow writing the next number because that represents the next half-life you just did, and this will help you keep track at the end to make sure you know how many half-lives you're undergoing to get your answer. Now, you're just going to continue, so 272 divided by 2, 136, and then draw your arrow there, and remember to always add your number to keep track, so 68, and then divided by 2 is 34, divided by 2 is 17, and so we just got to 5 half-lives, and if we remember, we did 15 divided by 3 to find how many half-lives we're looking for, and the answer was 5. So once we reach 5, our answer is here. So our answer in this case would be 17. How to calculate the half-life from a count rate is a little different. So an example of this type of question would be the count rate of a material is 2016, after 35 days, it has fallen to 63. What is the half-life? So once again, we were given some really important numbers within the actual question. The first number we are given is the count rate of the material, which is 2016. That is a really important number. We are also given the amount of time that has gone by for this certain material, and that number is 35 days. And the last number that we are given is the final count rate of the substance, and they are telling us that it has fallen to 63, from 2016 to 63 in 35 days. That is what it is asking us. So once again, we are going to use a box method to figure out what exactly is the half-life of this certain material. So you'd start with 2016, put a box around that, arrow, and make sure to always add your number so you can keep track of how many half-lives you've gone through. So then you will continue to divide by 2, just like the previous one, until you reach the final number it has fallen to within that amount of days. So in this case, we will stop once we reach 63 because it is said it's fallen to. So after dividing all of those up by 2, we finally reach 63. So going from 2016 to 63, there are 5 half-lives that need to take place. So by doing that, by getting that number 5, we know that if 5 half-lives take place within 35 days, each half-life is worth 7 days. And we find that by taking 35 and dividing it by 5 to get 7 days. Because 35 is the total number of days and 5 is the number of half-lives we have to go through to get 63. So to find how long a half-life will last, we take the 35 and divide it by 5 to get 7 days, which is how long this certain material per day undergoes a half-life. So the next really important thing in half-lives is carbon dating. So what carbon dating is it's a method of radio dating which is used to date rocks. So one question that's really important is, how is carbon 14 formed? So it is formed in the upper atmosphere by cosmic rays acting on nitrogen at a constant rate. The carbon-14 which is formed is radioactive and decays to produce nitrogen again. There is therefore a fixed amount of carbon-14 in the environment, which is a balance between the rate at which it is formed in the atmosphere and the rate at which it decays back to nitrogen. So how does it work? So all living things take in carbon from the environment. So just imagine people and the little puppy, and they're all breathing in carbon. Now, plants also are a part of this, and this is like a terrible flower, but it also breathes in carbon, or it doesn't breathe in, but takes in carbon during the process of photosynthesis, and in turn they release oxygen. So because of this, all living things contain carbon-14 at the same amount which is present in the environment. This amount is really small, and only 1 in 850 billion carbon atoms are the isotope carbon-14 present. The others are not radioactive. So when a living thing dies, it stops taking carbon from its environment, and the amount of carbon-14 in it will start to drastically decrease as the carbon-14 slowly decays. The further back in time that something died, the less carbon-14 that would be present in it today. The half-life of carbon-14 is 5,730 years. So measuring the amount of carbon-14 in a sample today can tell you how long ago something died, and therefore the age of a sample. It is very useful, but it also has some limitations.